Welcome, dynamics students. In this lecture, we're going to be extending our treatment of rigid body planar motion, velocity, and acceleration of 2 points on the rigid body and relationship to that rigid body's angular velocity and acceleration relative to a fixed reference frame to the particular case of rolling. So with rolling, we've got a rigid body that's moving in a very particular manner versus a fixed surface, and we can consider that fixed surface to be our fixed reference frame. So rolling wheel is our body B, our rigid body B, and whatever surface it's rolling over, we can consider it to be our reference frame F that we've been using for fixed reference for deriving equations for velocity of points and acceleration of points on rigid bodies under motion. Okay. What is rolling? So if we have two rigid bodies, B1 and B2, it's our favorite symbol for the rigid body, and they're rolling, then the following are true. So here's the criteria for rolling. Most important, a continuous sequence of points on the surface of B1 comes into a one-to-one contact with a continuous sequence of points on the surface of B2. So in this case, if you look down here, B2 could be the surface. B2 could be another wheel, so that's the case for gears. So we don't have the same point, it's not a fixed pivot, but we've got a different point on the circumference coming into one-to-one contact with a point on the circumference of the contacting wheel, surface, whatever. The one that we will use to write all our equations from is number 2. At each instant, not all the time, not like a fixed pivot, at each instant, the contacting points have the same velocity vector. So V at the point of contact on the rigid body equals V at the reference surface at that same point. Or V of the other rigid body, if we're talking about relative velocities of two rigid bodies. So same velocity. And because of that contact point is by definition an instantaneous center of zero velocity, which is something that we've covered in previous lectures for this course. So the contact point has zero instantaneous velocity relative to the fixed reference. Same velocity, surface and rigid body. So let's take a look at scenario 1. We're going to blow this up a little bit, make it easier to see. So we're going to derive some equations for the velocity of the center point of a rolling wheel, the velocity of our instantaneous center, which we know is 0, but we're going to look at how that relates to other things. And then we're going to take the time derivative of the expression that we derive and look at acceleration of the center, the instantaneous zero velocity point at the contact, and any other point. Because we know how to relate velocity and acceleration of any 2 points on a rigid body with respect to a fixed reference. Okay, so we got a wheel rolling. We're going to start with a simple case. A wheel is rolling on a fixed straight line. So here's our reference surface down here. It's a straight line. And we have a contact between the wheel and the surface at point A. C is our center point. And so we've defined positive x to the right and positive y downwards. So if we use our right-hand rule, we know that the z-axis or the k-hat axis is pointing into the screen, into the paper, and our positive direction of rotational velocity or acceleration is clockwise. So that's a little different than some other examples we've had so far. And we have a fixed radius of the wheel of r. It is round, it's circular. So point A has the same zero velocity as the fixed reference. Is fixed, zero velocity. So we can use our general expression for the velocity of 2 points on a rigid body with respect to our fixed reference to get the velocity of the center point, or any other point, but let's start with the center point. So V center is going to be VA, the point we know, which is 0, plus the angular velocity of the wheel in the k-hat direction crossed into the radius vector from A, the point we know, the velocity of, to C, the one we're determining. So A to C. So in this case, RAC is going to be negative because we're going up, and the rotational velocity will depend on whether it's rotating clockwise or counterclockwise. VA is 0. So we can write the expression as our angular velocity, positive or negative depending on clockwise or counterclockwise, crossed with negative r j hat, because we're going in the opposite direction from what we've defined as positive j hat. So k hat cross j hat, so k hat positive is into the screen. We're going to cross that into j hat. That takes us in a negative I hat direction, hence the negative over here. And then of course we had a negative sign on r to begin with. Those cancel and we end up with the radius of the wheel times the angular velocity equaling vc. So those are going to go in the same direction. So let's see. Let's see if this makes intuitive sense. We've defined a positive angular velocity as clockwise, so the wheel is going to roll this way, kind of like so. And if we do that, it's not hard to imagine, the points of contact are going to be going in this direction, so C should be moving in this direction, which is positive I hat. So notice it's a single direction. There's no j hat component to this. So an important observation is the center of a rolling wheel is actually undergoing rectilinear motion. It's going in a very straight line, I hat only. And of course, if we want to know how far it's gone, all we have to do is integrate with time based on our angular velocity. So the displacement of our center point, we can factor an r out because that's not changing, and just integrate theta dot with respect to t, and that will of course be a function of what our angular velocity with respect to time is. If it's this could be any function of time, but we'll end up getting r times theta at some time plus a constant to indicate wherever we started. And this will be a linear position. And notice our units are right. Theta is in some kind of radians, effectively unitless, and r is in length units. So our displacement or our position at any time for the center is going to be in length units. Okay. What if we wanted to know the acceleration of that center point? No worries. We're just going to take another time derivative. So we can start with the expression that we have for velocity of the center point and just take another time derivative. So our acceleration of the center point is the time derivative of the velocity of the center point. So we just take dt of our r theta dot, or omega, angular velocity, which we've determined in this case to be in the I hat direction, and r is a constant. I hat is in the fixed reference frame. So I hat's not going to change with time. The only thing that will is angular velocity, which becomes angular acceleration. So we end up with an angular acceleration also, or excuse me, an acceleration of the center point of the wheel is also in the I hat direction. So this is just like a rigid body moving in rectilinear motion, a translating body. So the center point of a rolling wheel translates. We don't have to, even though it is dependent on rotational components, omega and alpha, it itself is moving in a straight line versus the fixed reference frame. So that's kind of handy. That's something we can leverage as we go on. Now, to be fair, it is the only point on the wheel with rectilinear motion. So don't assume that any other point, even though we can apply this relationship for the velocity or acceleration of 2 points, we're not going to be able to have this neat rectilinear answer for any other point. So, and we'll see that as we go on. So it's only the center point that we can do that with. Okay, now we can go back. We know that A is a center of instantaneous zero velocity. How about acceleration? That's not always, doesn't always follow. Is it in translational motion? If you have no velocity, you don't have any acceleration. How about a rolling wheel? That's not going to be true here. Maybe for C, that's it, but definitely not for A. So let's focus on A and see if we can get an expression for the acceleration of our fixed point of contact with our fixed surface. So we're just going to go ahead and use the same strategy that we've used to find acceleration of any other point. We're going to break out our handy all-purpose acceleration of one point if we know the acceleration of another point and we know the angular velocity and acceleration of our rigid body with respect to our fixed reference. So that's going to be going to look like this. We've got acceleration of point A that we're looking for. This is acceleration of the center point, which we know. And then we have alpha times the radius vector from the point we know to the point we don't know, minus the angular velocity of our rigid body versus the fixed reference, times that radius from the point we know to the point we don't know. And this time we've got C to A. So our CA is going to be in the positive j hat this time because we're going down. We've designated downward as positive j hat. Okay, so CA is positive j hat. So we've got, again, K is positive going into the board or into the screen by the right hand rule. K hat cross j hat is negative I hat, so we get this expression for our cross product. And then of course we've got a positive j hat here. And oh, isn't that interesting? Take a look. These two are the same magnitude but going in opposite directions. The only term I have left is this one, and it happens to be pointing in the negative j hat direction, straight up towards the center. So the acceleration of our point of zero instantaneous velocity on a rolling wheel is actually normal to the path, and it's pointing back up towards the center. So, and this should look kind of familiar. This is akin to the centrifugal acceleration for a curved path. So we only have a normal component of acceleration at that point of zero velocity. There's nothing tangential. It's not speeding up, but it is definitely traveling on a curved path. And this is the acceleration expression that describes that curved path. Okay, so far we've just done nothing but leverage the expressions for velocity and acceleration of a point on a rigid body moving with respect to a fixed reference if we know the acceleration or velocity of another point on that body and we know the angular velocity and acceleration of that moving body with respect to the fixed reference, and we know a radius between the 2 points. All we did was do that plus impose the condition of zero velocity difference of the contacting point of a rolling body on a fixed surface. That's the only thing we added. So let's get a little more practice with rolling bodies, and we'll use the compass points. We're going to roll a compass down a flat surface. So we've got north pointing upwards, east pointing to the right, south pointing down, west pointing back over to the left. And we're going to define east as our positive I hat, and we're going to define south as our positive j hat. And so clockwise is our alpha and omega positive direction. So we're told that this rolling compass, which has a radius of 0.3 meters, at a given instant that we are concerned with, has an omega, an angular velocity of 2 radians, and because this little arrow is showing a clockwise rotation, and we've designated clockwise as positive, so we can say we have a positive 2 radians per second. But it's accelerating angularly in a negative, it's counterclockwise, 1.5 radians per second squared. So it's kind of, it's rolling clockwise, but something is slowing it down and trying to make it go back counterclockwise. Probably a moment being applied, I would imagine. We'll talk about the next chapter. We can think about it. And somebody wants to know, what are the velocities and accelerations of point N and E at that instant in time? Okay. So, and these aren't angular. Obviously, everything has the same angular velocity and acceleration, but we want to know the acceleration and velocity with respect to our fixed reference frame. Okay, so let's just start out. Let's start with a point that we know and move towards what we don't know. So let's start with n. So we can write our expression for velocity of 2 points on a rigid body. Velocity at point n is velocity at point S. I picked one where I knew the velocity, plus the angular velocity of the rolling compass in the k-hat direction crossed into a vector from south to north, okay, which is going to be going in the negative j-hat direction. So we're going to end up with positive 2 radians per second. We have a magnitude of twice the radius of our compass, and then we're going to have k-hat crossing into negative j-hat that gives us a positive i-hat. So there's our velocity of the north point. And we're going to make it a little bit easier for ourselves to do other manipulations. We're going to get the velocity of the center point because it's useful for some other things. So same. Use that point of instantaneous zero velocity at the contact at S to calculate our center point velocity. It's going to be almost the same as we did for north, except we have half the magnitude, same direction. So here's our expression for the velocity of our center point. So we're going to have 0.6 radians per second, whereas we had 1.2 up at the north. Now, because the center point is undergoing rectilinear motion, it's really easy to get the acceleration of that center point. Remember, we're going to want one point where we know the acceleration to apply our relationship for acceleration at any 2 points on a rigid body with respect to the fixed reference. So let's get the center point. So we know that the acceleration of the center point is just the second time derivative. So we can take the time derivative of the velocity, which we just did. So that's just going to be 0.3 meters times alpha, or omega double dot, second time derivative. Angular acceleration, which we know is negative 1.5 radians per second. So we end up getting negative 0.45 radians per second when you multiply these two. Okay. So let's use our expression that relates the acceleration of any 2 points on a rigid body to get the acceleration of up here at the north point. So we're going to have acceleration at a point that we know, which we just calculated at the center point. We got alpha, we've got a radius from the center point to n. So let me erase our previous one here. So from the center point to n, we're in that negative j-hat direction. We're going to go 0.3 meters. And we already know omega, and we already used that, so we crank that through, and we find we have two components. So we have an i-hat component, and we have a j-hat component, which is expected. The only place we really expect to have a single components of acceleration are going to be down at S and at C, and those are going to be 90 degrees apart. Okay, well, if we followed this procedure for n, we can follow it for any other point on the rigid body. Let's apply that relationship to get point E. So we'll follow the same procedure. We'll add the acceleration of a point for which we know the acceleration. We'll use the center point again. Alpha times in the k-hat direction, which we know, crossed into RCE. Okay, what direction is that going? Notice direction gets to be very important. We got a lot of cross products here, so the number one place you can make a mistake here is with signs, or which way we're looking from a reference. So if we draw a vector from C to E, it's going in the positive i-hat direction. So if we're going to cross K, which is positive going into the screen, cross with positive positive I, we're going to end up with a negative j direction. I think, no, positive j, because positive j is going down. We're going to go into the board, going to curl our fingers in the direction of I hat, and our thumb is pointing in the direction of j hat, or of the cross product, which happens to be positive j hat going downwards towards the south. There you go, see? Careful with signs. What's in your notes is correct, so you can use that for reference. And then our last term is just the square of our angular velocity, and then that same vector in the positive I hat direction. Of course, we're subtracting that. So all we do is add terms, and we have an expression for AE. Again, we've got an I hat and a j hat component to it. Different signs, different magnitudes. And I think, oops, we needed to get velocity for E. Acceleration was hard, so by comparison. So velocity, we'll just return and grab that. So we can use, again, the invariant point. We could have used the center point velocity. Honestly, it might have actually been easier, but if back up here we hadn't yet calculated that, so we can just use our point of instantaneous zero velocity at S, and then add our angular velocity in the k hat direction crossed into S. Let me erase that. A vector that connects S to E there. And so that's going to have a component of 0.3 meters in the positive I hat and 0.3 meters in the negative j hat here, because it's going up. So I just do that cross product, multiply by my angular velocity, and this is my velocity expression at E. So this is good practice in just applying our 2 points. And the only difference between this and any other condition of rigid body motion where we already know the angular velocity and acceleration is we have that invariant, I call it invariant, the point of instantaneous zero velocity. There is no variation in velocity between the rigid body and the surface at the contact point. That's the only additional piece of information that we use. Beyond that, all we're doing is using our very general relative motion of a rigid body versus a fixed reference. Okay, well, what if we're not rolling on a flat surface? Now we have two curved surfaces. And I'm going to blow this up a little bit again so we can see all of our subscripts and whatnot. Okay. This works exactly the same as a flat surface, except we need to switch over into our convenient tangent normal coordinate system to take into account the path that we're following on this curved surface. So kinematics are the only thing that changes, and the coordinate system will take care of that for us. So let's look at what we have here. We're going to use, and the one tricky thing is we're going to switch between coordinates for the rigid body, which is we're going to look at a tan normal, but we're going to reference that to a Cartesian out here in the fixed reference plane somewhere, fixed reference frame, excuse me. Because we want to use tan normal for these two relative surfaces. So we're just going to reference everything to an IJ, and that will make it easier in the long run. But we definitely need the tan normal just to represent this surface. So here we've got I hat or X increasing to the right, and we have J increasing to the left, which means that a clockwise rotation here of omega or alpha is positive. So I hat positive, it's going clockwise. So we've got a few features here. In addition to the center of our rolling wheel and our contact point, which has zero velocity relative to our curved fixed surface, we've also got what we call a rho, which is the distance between the wheel's center of a rolling rigid body wheel's center point, and the radius of curvature of our surface. So if you think about it, we can draw, you know, assuming that it's a constant radius from this point. This would be our radius of curvature of the surface, and the distance between that and our center point we're calling rho. So it's a distance. It isn't the entire radius of curvature of the surface, so it's the offset between those two. Okay, but beyond that, everything else is the same. So let's just write an expression for the velocity of our center point again, which is a good starting point. And we're going to write it and give it and express it in tangent and normal coordinates. So tangent is going to be a tangent to this surface at this point, and normal is going to be normal to the surface, and that normal axis is going to go up through the center point and also intersect the radius of curvature point for our surface. So everything's going to be on that E sub en hat. Okay, so what do we start with? Well, we know that point I has zero velocity, so let's use that as our known point. This is really the only one we do know. So we add our angular velocity in the I hat direction. We're going to cross it into a radius vector from the point we know to the point we're looking at. So it's R I to C, which is going to be in the positive normal direction because we've defined our normal axis as positive. Notice that's opposite of J. The two aren't even perpendicular yet, so we're not going to try to relate them now. So we do the cross product, and we're going to cross K, which is positive going into the screen, with N that is positive going normal, and we find that our thumb is pointing in the positive tangential direction. And so we have a magnitude of the radius of the wheel times the angular velocity of the wheel and being directed in the tangential direction, which is kind of reassuring because the wheel should be rolling. This center of mass of the wheel should be following a path that is parallel to this surface. So a tangential direction for that center velocity is pretty reassuring. Okay, let's figure out the acceleration of the center. Take the first time derivative. So we're going to take this expression, take the first time derivative. Now we're taking the first time derivative with respect to a reference frame with these axes. So this time our tangent unit vector is not going to stay constant with time. So that's going to be the difference in the straight line rolling. So remember, the tan normal is like cylindrical coordinates, where our R hat or theta hat or our tan hat, normal hat, when we look at their rate of change, the rate of change of those unit vectors is always perpendicular to the original unit vector. Not so true of the others. So we're going to see that here. So let's go ahead and take that derivative. We've got the derivative of a product, R theta hat, or excuse me, R theta dot, or omega, I'll call it, angular velocity, and our unit vector in the tangential direction. R is not changing, so we're going to get the sum. We're going to be taking the first derivative of a product. We could factor out R. So we're going to get alpha theta double dot in the tangential direction, which is reassuring. That's what we're used to with a tan normal coordinate system. Then we're going to have R theta dot times the first time derivative of our tangent unit vector, which we know from our particle kinematics is S dot over the radius of curvature of the curved surface. Okay, and S dot is our velocity along the path. Okay, so we know that since our center is following the path, because it's traveling in the tangential direction, we can relate the magnitude of S dot to V sub c, which we just wrote an expression for. And so we end up getting an R theta dot squared over rho for our multiplier in our normal direction. So here's our expression for acceleration of the center point of our rolling wheel if we're rolling on a curved surface. Okay, notice the big difference versus the flat surface is we've now got this other component. If we were on a flat surface, this would be pointing in the I hat direction, and there wouldn't be anything else. So what this other component is doing is basically accounting for the acceleration necessary to keep this center point moving in a curved path. So again, this would be akin to a centripetal acceleration. The acceleration needed to keep this going around rather than just going straight. Okay. So let's look at the acceleration of some other points. Now that we have the acceleration of the center point, let's use our handy dandy acceleration of 2 points on a rigid body that is moving relative to a fixed reference frame. Let's go for the point of instantaneous zero velocity down here at the bottom. Let's write an expression for its acceleration and see what it is. So we'll start with the acceleration of the point we know, a sub c, add the angular acceleration of the body, alpha, the k hat direction, crossed into the radius from the point we know to the point we don't know, minus angular velocity squared, same radius, point we know to point we don't know. And in the case of what we have here, a radius from C to I, let's look back at our signs, n hat, our normal unit vector, is pointing away from C. So if we have a radius vector from C to I, it's going to be in the negative en hat direction. So it's going negative to E sub n. So that's going to get inserted in here and in here. So, and we can use our expression for a sub c from up here. That comes down. Here's a sub c that we just derived on the other page. And if we execute the cross product and we add this term, we end up getting these other two terms. So r hat crossed into negative r e n hat. We're going to end up with something in the tangential direction. So k hat cross en, your thumb's going to point in the tangential direction. And then of course we have our angular velocity here and our c to I there. So we can collect all the terms in the tangential direction on one side, all the terms in the normal direction. We can group them all and see what falls out. So let's see if we find anything common. Oh my goodness. Those two cancel out. Ooh, once again, just like the case of the straight surface, we don't have anything in the tangential direction when we look at acceleration of that invariant point. But we don't have the same magnitude. If we factor out our unit vector in the normal direction, which would have been the j hat direction for a straight surface, instead of just having one, we've got this extra term. So this actually this is always positive. So our acceleration at the point of instantaneous zero velocity for a curved surface, for a wheel rolling on a curved surface, is always going to be a bit bigger than it is for the straight surface. And again, we need that extra acceleration because not only are we accelerating that point on the wheel around the curve of the wheel, keeping it going in a circle, but the center of the wheel is also going in a curved path. So you have two things that need to curve. So you need extra acceleration to curve them around, is one way to think about it. So here's a comparison of the two. R is the same. The square of the angular velocity is the same, written a little bit different way. You've got 1 in one case, and you've got effectively R over rho plus 1. Negative sign. Why do we have a negative sign in one case and not the other? Because J and E sub n are going in different directions. They're pointed effectively in the same direction, but we've defined E sub n up here going up. We've defined J going down. So they are equivalent, but there's the negative sign from having been derived in a different reference system. Okay, so if we're looking at maybe constructing bearing surfaces for two rolling wheels, like a ball bearing in a race, the surface of that bearing race is going to have to exert a force to satisfy that normal acceleration. So we can expect for the same mass that we're accelerating around, we're going to expect higher forces necessary to get it to do that. So that might have some implications on material choices or thicknesses or surface treatments. So that gets important, especially if we have something that's going very, very fast. If you can think about it, if this starts to get very, very large, then this number will get very, very large, and having anything else multiply by it only makes the problem worse. Okay. Well, let's continue to use our favorite expression for the acceleration of 2 points on a rigid body. And let's look at the point up at the top. Let's look at point Q. We can follow the same procedure starting with our known acceleration of point C, and then use basically what's going to end up being the opposite of our radius vector. We've got the same alpha, we've got the same omega, but this time instead of going from C to I, we're going to go C to Q. So that's going to have a positive. That's going to be R C to Q is going to end up being little r radius of the wheel in the positive enormal direction. And so we're going to get a different sign out of that cross product. And so as a result of that, everything else looks the same, except we end up having a negative sign here in this portion. So that's the only difference between basically Q and I. Otherwise, excuse me, plus you actually have a tangential component too. It's flying along pretty fast in this direction, as well as having to curve around. Got a tangential component there. Okay, so we can imagine different scenarios for the radius of our rolling wheel and the radius of curvature of the surface that we're rolling on. So this is the kind of oddball case of the wheel, the rolling wheel, moving rigid body has a bigger radius than the radius of curvature. The thing that it's, or not the radius of curvature, but the distance between the wheel's center and the radius of curvature of the curved surface it's rolling on. So r greater than the rho defined here. And that looks like this, where the wheel will roll around basically inside this race. And so there's certain types of gears that will do that. R can be, when R is less than rho in this case, the difference between The radius of curvature in the center point, we have what we've already derived, which is this case over here, but we can also have a convex surface, which oddly enough works the same way, because rho ends up being positive, a positive distance, regardless of whether it's being measured from down in the surface or out above it. So we end up with that same 1 plus r over rho added to the acceleration, the normal acceleration for our invariant point. So generalities for straight versus curved paths. So we can kind of make ourselves a little table here. And relationships between the wheel center and contact point of the surface are instantaneous zero velocity center. So for velocity of the center, that's going to be equal to our angular velocity of the wheel cross our IC plus no normal portion if we're rolling on a straight surface, and an A sub c, again, we're just walking through our formula, alpha k crossed into our IC plus a normal component for acceleration, and the value will depend again on the relative natures of r and rho. In the case of curved surface, it would be it would be 0, or this part would be 0. Excuse me, if we had a back up. I'm mixing up variation in r and rho versus straight and not straight. This part will be center point acceleration. No normal component if it's straight. Rectilinear motion. Center point will have both tangent and normal in the case of curved surface, and what its value will be depending on the relative values of r and rho. So velocity, no difference. Acceleration, difference. Straight surface to curved surface for acceleration of the center point. So, and in both cases, we're looking at velocity versus or acceleration of the center point using our point of invariant zero velocity at the contact point as our reference point. So we don't have a term out here. Okay. Generally speaking, just remember more acceleration needed to go around that curved surface. But otherwise, once again, we're just applying 2 points, rigid body motion versus a fixed reference, and using conditions of rolling, either a straight surface or that tan normal expression to bring in the expression for a curved surface. Really, there was no difference between straight surface, curved surface, other than we used a tan normal coordinate system, and it was that tan normal coordinate system that brought in all of the radius of curvature and other expressions that we ended up having. Okay, I'll zoom out here. We can see more of the problem. So let's do an example where we put this to use, and I am going to warn you, I am not going to step through all of the geometry, which unfortunately is a huge part of this particular problem. You can work it for yourself if you would like, and use my answers in these notes to check yourself. But it does draw on what we've just done. This is just velocity. So we have two cylinders, C1, and this is kind of a scripty C to remind us that it's a rigid body. Okay, so it's down here kind of in this curvy trough. Rolling on a curved surface. And C2 is another rigid body up here, and it's rolling on a flat surface. And they're connected by a bar, B, with a scripty B, which is a third rigid body. Anytime you see a scripty letter, think rigid body. And they're rolling on surface S, which is the shaded surface here. And we know the angular velocity of our bottom cylinder, 0.5 radians per second. We've defined our coordinate system. So counterclockwise is positive rotation. So basically C the bottom C1 is rotating counterclockwise at the instant shown. And somebody wants to know the angular velocity of the bar and the velocity of point E over here on the edge of the rolling cylinder on C2 at the time shown. So, strategies looking at this. Oh, excuse me. We were told that the angular velocity was clockwise. I'm wondering why I had a negative sign there. Counterclockwise is positive. We're told the rotation is clockwise, therefore negative. So that's just rewriting our angular velocity with our k coordinates. So it's negative 0.5 radians per second k hat. So we can use that to get an expression for the velocity of c. Why was that important? Because that gives me a known velocity on one point of that bar. And once I know the velocity at one point on a rigid body, I've got a good chance of being able to find both the angular velocity and the velocity at another point. So I go ahead and use that. So I use my general expression for velocity at the center point of a rolling wheel. So that's my omega k crossed with my invariant point to the center, which is positive 0.4 meters. The radius of each of those cylinders being 0.4 meters. So now I've got the center point velocity of C1. Got an expression for that. Okay. Now I'm going to leverage that to get Q. Velocity of the center point of the other cylinder and a second point on bar B. So here's my general expression for velocity of 2 points on a rigid body. VQ is going to be VC plus the angular velocity of the bar, not one of the cylinders, the bar, k hat crossed into radius vector from the point I know to the point I don't know. And I can express this radius vector using the geometry of the problem, which, warning, is not simple. There's a lot of little distances to add up because of that curved surface, but it does add up to this vector going 1.7 meters in the I hat and 1.53 meters in the J hat. Radius between those two. So I can drop in my expression here for VC and write this. Now I have two unknowns. I have VQ that I don't know, and I have omega B for the angular velocity of the bar. Now what I do know is point Q. I got another piece of information. It's a center point of a rolling wheel, so it's going to have rectilinear motion. So I can tell that it's going to follow basically parallel to the surface that wheel has to roll on. It's going to be going in this direction. VQ is going to follow this surface. 45 degrees. So I may not know the magnitude, but I sure know the direction. So, and it's got an I hat and a J hat component. So now I have two equations effectively from this expression, and only two unknowns. I have the magnitude of VQ and I have omega B. So what was key? Lots of key. We're combining a lot of the characteristics of conditions of rolling. We've used the invariant point to get our center point rotation. We've used the fact that a center point of a rolling wheel follows rectilinear motion, so that gave us our direction for VQ. And we've used again and again our relationship between 2 points, velocity of 2 points on a rigid body. Okay, so this will end up giving us angular velocity of our bar and velocity of our point Q, which were two things wanted. And once we have the velocity of the center point of our second cylinder, we already knew the angular velocity of that second cylinder. We're home free to get the velocity of any point on that second cylinder. So I actually did this in 2 steps. I calculated the velocity of the contact point with the surface on that second cylinder. I went ahead and I used the velocity of point Q to get the velocity of the invariant point, and then I in another step I used the point of instantaneous zero velocity at the contact as my known velocity point to get the velocity at E. So that was a 2-step. So first calculated the contact point at cylinder 2, its velocity, and then use that to get VE. Actually, I calculated them both independently. Never mind. You could do both. I think I changed my mind partway through and decided that it was easier to use the center point Q than to get a radius vector from point I to E. You could do it either way, whichever one has the easier geometry. So that's 2 different ways. Okay. Oops. Okay. We'll do another example where we have to use, I think this one will involve some acceleration. So we have a curved bearing surface with a radius of 1.2 meters, and we have a rolling wheel rolling around on the inside, and it has a radius of 0.3 meters. So we're going to have a difference, our rho difference in the 2 points we're going to find down here. The distance from our radius, our radius of curvature of our surface to our center point of our rolling wheel that we saw in the derivation. This is rho for this problem, and we'll see that further down in the problem. So we have a rigid bar that's hinged at the center point of our rolling wheel, and then it slides along the bearing surface otherwise at B. So 2 rigid bodies, one rolling and one just fixed and sliding. We've defined x positive to the right, y positive going up, and rotation is positive counterclockwise. And we're given a rod length, we're given a wheel radius. Okay, so we're set. A small cylinder rolls on a track. The small cylinder angular velocity, 5 radians per second k, so it's positive k hat, counterclockwise rotation, and it's got an angular acceleration, also positive, 0.2 radians per square second, or second squared. And this is when E is at the bottom of the track. So everything is instantaneous. We know those angular velocities and accelerations at that point. Rod R is pinned at the bottom and it's sliding up at B. And someone wants to know the velocity and acceleration of point B. So we're gonna relate points again. We're gonna use characteristics of acceleration and velocity of 2 points on rigid bodies. We got 2 rigid bodies again. We're going to consider acceleration as well as velocity, and we're going to bring in our rolling criteria. And of course, we're rolling on a curved surface. So we know something about what's going on with cylinder C because we have more information. We know it's rolling. So the fact that we know it's rolling gives us a lot more information to start with, so that's where we have to start. So let's kind of zoom in on that. So here's our rolling on a curved surface. So this looks exactly like the scenario that we derived. And here's a really handy point. At the point that we're looking at here, we're at the bottom of this curved surface. So in fact it's specifically spelled out. Our rolling wheel is at the bottom of the track. And we've defined a vertical horizontal coordinate system that would, where the vertical would go through the bottom of the track. So for the instant we're concerned with, it's really handy. Our tan normal coordinates can superimpose with an I hat, j hat. So that'll simplify our calculations. So, and I've put a note here just to remind myself of my tangent unit vector equals my I hat, and my normal unit vector equals my j hat. Now, if you're going to flip back and forth in the notes and go, I want to refresh myself on the derivation of this curved surface acceleration, take note the j hat axis may or may not be pointed in the same direction. So be careful to look at which way it's pointed for this particular problem, or the signs won't necessarily add up. Okay, with all of those precautions, we'll just go ahead and write an expression for the velocity of our center of our rolling wheel. So we can do it in terms of the point of instantaneous velocity at the contact down here, which we know is 0. So we use rotational velocity of the wheel, which we've been told, k hat crossed into the radius vector from the contact point up to the center, which is going to be in the positive en, positive normal unit vector direction, and positive j hat. So k hat is positive coming out of the board. If I cross that into j hat, my thumb's pointing in the negative I hat direction. So velocity of my center point is negative 1.5 meters per second in the tangential direction, and negative 1.5 meters per second in the I hat direction, since Etan and I hat are the same. Likewise with my acceleration, we're going to have r times alpha instead of omega, because we're looking at acceleration. It's a center point, it's rectilinear motion, and we're going to have that same negative tangential hat because we're going to be basing on that same cross product. You could also think of it as this negative sign is following your unit vector, and you're just going to take the second time derivative of your angular position and get alpha. So we're going to have a negative sign on that first part of AC. Because we got a curved surface, we've got a normal component, so we've got our radius of the small wheel, angular velocity, which we've already used up here, divided by rho, and rho is of course the difference of the position of our radius of curvature of the track, or of the surface we're rolling on, with the radius of our wheel. So that won't be rho of the surface, it's that difference. So we can drop in values for this formula on the next line. So this is that. So r is 0.3 meters. Our alpha E with a negative, we're going to have negative 0.2 radians per second squared, tangential direction, same as I direction. And now we're going to populate up here 0.3 meters. We're going to have 0.5 radians per second squared. This really shouldn't have a negative sign on it, so we'll get rid of that. I believe that's an error. It wouldn't matter because it's going to get squared anyway. And here's rho, the difference between our our radius of curvature and our center point of our wheel. So that's going to end up being 0.9, and we get this expression for the acceleration of our center point. And so we could again replace that tangent normal with an I hat, j hat, but only because the wheel is in that downward position directly at the bottom of the curve. Okay, so having A sub c and V sub c, we now have both the acceleration and velocity of one point on a rigid body. And we know something about the motion of B. B is just going to follow the path that it has to glide on. So at this point, B can't move into the surface because the surface it's sliding on a rigid surface, so it can't do that. So B's motion is going to be following tangent to that curved surface. So B is only going to have velocity in the j hat direction because a tangent to the surface here is in the j hat direction, positive y. Okay. So we can work, again, the same 2 points. If I want to know the velocity of point B, I've already got the velocity of point C up here. I don't know the angular velocity of the rod, but I do know an expression for the radius vector from point C to point B. I can just use the geometry of the problem, a little bit of trig, remembering to subtract my 0.3 meters from a 0 point radius vector. So I can very easily get an expression for the velocity of B, and it ends up being negative 0.2 meters per second. And I can use the fact that this expression will give me 2 equations, one in the I hat, one in the j hat. I also get an angular velocity for the rod. So that's 2 things we needed to know. So we now know angular velocity of the rod, and we know the velocity of point B up there on the surface sliding. Now repeat with our equations for acceleration. Okay, we're back from a little editing pause. So at last look we had just calculated the velocity of point B, which, because B is riding on that surface, its velocity is tangent to that surface, and as such it only has a component in the j hat direction, and we found the angular velocity of our rod. So we can then insert those, one of them anyway, into our general expression for acceleration of 2 points to get our acceleration of B using our already determined acceleration of point C, and a radius vector from C to B, which again we can get from the geometry of the problem. And so this will end up generating one unknown, the acceleration of our rod, and then we're going to have 2 unknowns for our acceleration of B. Unlike the velocity, which only has one component because it's tangent to the surface, acceleration doesn't necessarily have to be tangent to the surface, but we can write an expression for it because it's like going along a curved surface. Acceleration of anything going on a curved surface is going to have a tangent component, which in this case at that one point is in the negative j direction, and then it's going to have a normal component. In this case we're talking normal to that surface, and we'll have the velocity, in this case of B, along that surface, which we've already calculated. This is VB. And I'm going to erase what I just drew so I can make a really important point about rho. I've now dropped back to my standard convention for a tan normal coordinate system. Rho here is 1.2 meters. This is not the rho that is the difference between the radius of curvature and the center point of the rolling wheel that we had up in our expression for acceleration of points in the rolling wheel. This is the rho that's used just for acceleration in the normal direction of anything following a curved surface. So it's 1.4. So by using this second equation, I can now solve for both components of the acceleration of point B, the I hat and the j hat, because in this case, conveniently, we're in another orientation where our tangent and normal coincide again with I hat and j hat, except opposite than what we did down at the bottom. So we do literally a 3 equation and 3 unknown effectively, and we solve for the components of A and of the acceleration of B in both directions, and we also solve for the angular acceleration of our rod B, and then we get answers for what we don't know. We really end up just having 2 unknowns, but we we could have solved for this one. We have a second equation because we have this direction. Okay, a little bit long and wordy problem there. Major points that we had: establish a coordinate system, establish direction of positive or negative rotation. The switching back between the tan normal needed to deal with this curved surface, both for the rolling motion and then again in order to solve for our acceleration at point B, because B is following a curved surface, were probably the cruxes of the exercise. Otherwise, it was simply plugging into our expressions for velocity and acceleration of one point of a rigid body when we know the velocity or acceleration of another. So it's that switch between I hat, j hat, and our tan normal at two different points, and of course knowing which row we're using depending on whether we're looking at a wheel rolling on a curved surface or simply something traveling along a curved surface without rolling. Okay, last topic in rolling, and the last topic before we get into relative motion of rigid bodies, and that's gears. This is very, very short, but it's an often used concept, and it basically relies on the fact of our zero relative velocity at a contact point. So we've looked at rolling wheels on flat and curved surfaces so far, and we've noted that the contact point between the rolling surface and the rolling wheel has no difference in velocity. Well, we can have two wheels roll on each other and still know that basically the velocity at, in this case at point P on our large rolling wheel, is the same versus a fixed reference frame as the velocity coming from our smaller gear. So now we're looking out to a fixed reference frame and saying, yep, velocity of this point is the same as the velocity coming from this point, by definition of rolling, because they are effectively rolling on each other. Okay, if we write an expression for the velocity of rolling gear 1, it's just simply r1 times its radius times the angular velocity, and that's the same for the second. And so equating these two means that we have a relationship between angular velocity and radius. And if we take the first time derivative, we see that we have the same kind of relationship for acceleration. So they're in a ratio. So I am not going to go over this example verbally because it's fairly self-explanatory, I think. But a bicycle gearing system is one of the most classic applications of the idea of gearing and matching velocities and inferring angular velocities. And in this case, we're just looking at velocity, but I'll kind of set up for it. You have a bicycle wheel, and we have a picture of this rear wheel. It's a 13-inch radius, so it would roll on the ground down here. And it's moving forward at 176 inches per second, so that's the center point velocity. And so we can use the radius of the wheel and the center point velocity relationship to get a rotational velocity for that back wheel, which will be the same as for the back sprocket because the two are bolted together. They're rotating together. The trick then is to use what we know about the number of gear teeth in the front and the back to get information about angular velocity of the front and the back sprocket that are connected with a chain. And so you can think of gear teeth as relating to radius. So if we have 26 gear teeth versus 9 gear teeth, you could say the ratio of the radius of the front to the radius of the back is 26 to 9. So that's the key to solving this. So we end up having to set up an expression that relates velocities at contacting points being the same with that radius ratio via the gear teeth with the ratio of the angular velocities. And the important point to remember here, this is kind of a throwback to our Unit 1 related rates. These two gears they're meshed indirectly via a chain. But if you take the fact that the chain between points D and F doesn't stretch, then the velocity of point D and the velocity of point F match, just like point P on these two meshed gears. So you can use that relationship to relate velocities of these 2 points on these two different sprockets or gears, and having a ratio of their radii, you can get a ratio of their angular velocities, which is what was asked for in the question. So that concludes our discussion of rolling, various flavors of it, but basically rolling is just another planar rigid body motion. We can use everything we know about relating the velocity and acceleration of one point on a rigid body to another point on that rigid body via the angular velocity and acceleration of that body relative to a fixed reference frame. And the only tricks are going between a fixed rolling surface and then a curved surface where we have to pull out our tan normal and be careful about not making assumptions about acceleration ever being zero when we have curved surfaces. Just work straight through your equations. Invoke what you know about the kinematics of motion on a curved surface. If you have to turn back to your particle kinematics to remember that, go ahead and do it. There's nothing wrong with that. Don't necessarily treat a rolling wheel like a particle, but you can know the motion on a curved surface. So go ahead and follow that. And then gears are super simple. You know, basically contacting points are not moving relative to one another. There is no slipping. And as a last note to rolling, there are some books that will talk about rolling with sliding and some kind of combination. From the standpoint of what we're studying, the entire concept of rolling hinges on that point of instantaneous zero velocity at the contact. So if there's sliding, everything we've just done in this rolling section goes out the window because our basis assumption is now not there. So if someone says you've got a wheel that's rolling but it's sliding on the surface, you can't use anything that we did. It's effectively sliding. If it happens to be rotating too, fine, but it's not rolling according to the definition we're using. So just as a caution. So if somebody says I have a wheel that's rolling, you might want to say, is the contact point same velocity as the surface at all times? And if they say yes, then everything here applied. So next discussions will dive into relative motion of rigid bodies. So we'll look at relative velocity and acceleration where we got two bodies moving in a fixed reference frame and looking at their motion relative to each other via that fixed reference frame. So stay tuned.